Have you ever thought about what the ultimate cold would be like? A temperature so unbelievably low that everything, and I mean everything, just stops? Well, that's the quest for absolute zero, and it's one of the most fascinating and maybe impossible goals in all of physics.
Okay, let's just dive right into the big question. It seems pretty straightforward, doesn't it? We can make things colder, so why can't we just keep going until we hit the absolute bottom? As it turns out, the answer takes us on a journey from our everyday intuition into the totally bizarre but brilliant world of quantum mechanics.
You know, this is a fantastic starting point, and it makes so much sense on the surface. If heat is just the energy of particles, and you get rid of all the particles, well, you should get rid of all the heat, right? No particles, no motion, absolute zero. But, and it's a big but, it's just not that simple.
So, to figure out why that whole vacuum idea doesn't quite work, we first need to get a really solid handle on what temperature actually is. It's something we talk about every day, but at a fundamental level, it might not be what you think.
And here it is, the key idea. Temperature isn't some property of empty space. It's a property of the stuff, the matter within that space. It's literally the average energy of a bunch of atoms as they zip and move around. So if you have no particles, you have no motion to average.
I absolutely love this description. It paints such a perfect mental picture, doesn't it? Just imagine all the atoms in an object in this constant dance. The faster they wiggle and jostle and vibrate, the hotter it is. And the slower they move, well, the colder it gets.
And that right there is the punchline for our vacuum idea. By sucking out all the particles, you haven't reached the coldest possible temperature. You've just removed the thing that has temperature in the first place. It's like taking the thermometer out of the room. There's nothing left to be cold.
Okay, so if a perfect vacuum doesn't work, what's stopping us from just taking a single particle and slowing it down, down, down until it's perfectly still? Well, this is where we have to leave the physics of our everyday world behind and step into the quantum realm. And a fundamental rule that says nothing can ever be truly still.
Now, the phrase "a physical impossibility" is so important here. This isn't about having better tools or more precise instruments. The Heisenberg uncertainty principle is a core feature of reality itself. It's like the universe has a fundamental fuzziness built into its operating system, and we can never, ever get past it.
So let's just walk through this logic because this is where it all comes together. To get to absolute zero, a particle has to stop moving completely. That means you know its momentum perfectly. It's zero. Simple enough. But the uncertainty principle says if you know momentum perfectly, you can have absolutely no idea where the particle is. It could be anywhere in the universe, and that completely contradicts the idea of it being frozen in one single spot. You see the problem? The two conditions are mutually exclusive.
Reaching 0 Kelvin, absolute zero, means a particle has to be perfectly still at a perfect location. And the laws of quantum mechanics just look at that and say, nope, can't do it. The universe at its most fundamental level is restless.
This quote just nails it. There's always this leftover energy, this tiny, constant, irreducible quantum jiggle that you can never get rid of. It's actually called zero-point energy, and it's like the background hum of the entire universe.
You know, this idea of a limit you can approach but never actually reach, it's not the only one out there. In fact, it has a really famous cousin in physics, and it gives us a great way to think about this whole problem. Think about it like this. Trying to reach absolute zero is a lot like trying to push something to the speed of light. As you get closer and closer to that ultimate limit, the amount of energy you need to put in, or in our case, take out, just gets bigger and bigger until it approaches infinity. It's an impossible finish line.
And where does this light speed limit come from? Einstein's special relativity, of course. It basically sets the speed of light as the cosmic speed limit. It's non-negotiable. It's like a universal law of the road.
And just like in the quantum world, getting close to these universal limits has some truly bizarre side effects. As you get closer to the speed of light, time itself actually slows down for you. Distances shrink, and mass and energy become two sides of the same coin. These limits aren't just stop signs, they fundamentally warp the fabric of reality around them.
So, let's bring this all home. We started with what seemed like a simple question about a vacuum, and we ended up at the absolute limits of the universe. So, what's the big takeaway here?
All right, so here's the rundown. We've learned that temperature is all about the wiggles of particles, which is why a vacuum has no temperature at all. And thanks to the Heisenberg uncertainty principle, there's always going to be a tiny bit of jiggle left that you can never get rid of. That makes absolute zero an infinite finish line, just like the speed of light.
And that leaves us with a pretty deep thought, doesn't it? We experience the world as solid, stable, and still. But at its very core, the universe is a place of constant, unavoidable motion, a place that can never truly be at rest. It kind of makes you wonder, if we got something that fundamental wrong, what else do we completely misunderstand about reality?